So today we're going to look at the story about the decimal theme of the cyclic group theme, which are group themes where aggregation is important. Decimals are especially important for internal aggregation. Personally, it's true that I have a little trouble talking about decimals because, well, we can ask ourselves why we should obsess over this number, which is nothing special or extraordinary, but at least it connects with the man in the street and could also happen to you during a draw. So let's look at this. You have this number. So I don't know, it's starting to see it's a little bit of success, it's a little bit of fame. This number, I don't know if you know it. 1/4. There you have it. A success linked to decimals. Without base 10, it has no success, huh? But hey, it has this success. Why? Well, look, you multiply it by 2, and what will that give us? You have 2a, you do the carry. Over there, 5, 7, 1. There you go. And what do you see? Well, it's a cyclic permutation of this number 2, 8, 5, 7, 1, 4. Multiply by 3. And there we get 4, 2, 8, 5, 7, 1, which is another cyclic permutation of the first. You continue 4, multiply by 4, and there it works. By 5 it works again. And we're going to do all the cyclic permutations when we multiply a by numbers k from 1 to 6. We have the 6 cyclic permutations of this number written in base 10. You're going to tell me, well, we'll try 7. Well, yes. Well, when you do 7 times a, look, well, it's 6a, x plus a, and it's easy to see that you'll have 9 nines here, just 9 shot here. And that is to say, if you prefer 10 to the 6-1, it might be better to see it like this. It might be simpler. There you go. Well, this number with only 9s is not innocent. And let's look at the same number with only 9s. So it was a multiple of 7. But if you look closely, it's also a multiple of 13. So let's look at what we have left here. Let's start calling A what we'll call B. 7, 6, 9, 2, 3. I'm going to write it with 6 digits, even if it means adding a digit on the left. And so it's B equals 0, 7, 6, 9, 2, 3. Same thing. I'm going to try my luck at the multiplication game by multiplying by numbers from 1, well, this time to 12. Well, this time to 12. And here I'm surprised because I'm already starting by multiplying by 2 and it doesn't work. The magic is gone. Okay, let's not let that get us down. We have to multiply by 3 and then it comes back. We have 2, 3, 0, 7, 6, 9. Okay, let's multiply by 4. It works again. Multiply by 5. Oh well, it doesn't work anymore. But on the other hand, it's a cyclic permutation of the second number that we got by multiplying by 2. 3, 8, 4, 6, 1, 5. There you go. By 6, well, it's another cyclic permutation of this one. By 7, again, of this one. By 8, again, of this one. By 9, it's a cyclic permutation of B. By 10, also by 11. Well, of 2, and by 12 of B. There you have it. There you have it. So what do we do with this? Here we only have cyclic permutations of a single number, and here we have 2 numbers whose products we can obtain by cyclic permutation. So what is this related to? Well, it's related to the fact that modulo 7, let's look at the cyclic group generated by 10. Is that me? Careful, Z7Z star. Multiplicative group, I mean. So 1, 10 is 3, 10 squared is 2, to check 10 cubed is 6. Well, 6 is negative 1, by the way. 10 to the 4th is 4. 10 to the 5th is 5. And 10 to the 6th is 1. Okay, you can check it. It's easy. 10 is of order 6 in a group of order 6, which means that 10 generates Z. 7 is the stars. Now let's look at sesh 13 Z stars. So in Z of 13 Z star, you will see that the subgroup generated by 10, by the class of 10, 10, 10 squared. So that makes 110 is 1. And there you already have negative 1. So that means that it will be of order 6. And there you have the 3 and 4. It will be of 2 out of 6 in a chord group order 2. So it has index 2. Okay. So that means it has two classes. There are two classes modulo, the chord group is Z of 13. There are two classes modulo, the subgroup generated by 10. Okay. And the two classes, well, that's the subgroup itself. A, the class of any element that is not in the group. So I'm going to take 2, well, 2, which clearly is not in it. Oh, well, I have 2, 7, 5. So I look at 2 times 10. That's going to be 7, 13. 2 times, so here it's going to be 18. So 5, and so on. I just multiply by 2 here, and I get the second class, which means that with all that bingo, I have the entire group, Z13, Z star. Well, look, that's good, because 110, 9, 12, 3, 4 corresponded exactly to 1. Look here, 3, bingo, 4 bingo. No. He, 9 to bingo, 10 bingo. 11, no name, and 12, bingo. So, we have them all, okay? We have those that correspond to the permutation of B, and the others correspond to those that are permutations of 2B. There you go. So now we can start thinking about things in a certain way. We can come up with a theorem. Let's say P, so we want to be prime, okay? A pair tries to still have here a multiplicative group, in any case. Different from 2 and 5, because we want 10 to be in the multiplicative group Z over P, Z that star, I'm going to call n the order of 10 modulus P, okay? Well, here it was always 6. And I'm going to look the number A equals 10 to the n-1 lab P. That's exactly what we did here. So 10 to the n-1 is 1 A, and 10 to the n-1 over 13 for B. So Ka, I look at all the multiples of A for K, ranging from 1 to P1. That's what we did here. That's what we did here. Subdivides into P1 over number. So here, you're going to have, well, for n equals 6, we're going to have 1. Number, single number. And here we're going to have 2. So when I say numbers, it's actually an accumulation of decimal digits where we add or have to add what we need, like a 0 on the left to get exactly n digits. That's what we did here. So we have P1 over n numbers, whose n decimal places are equal to permutation. That's exactly what we have. So now I'm going to add a little codicil to the theorem, which is that in addition to the rank corresponds, that is to say, here module 7, you have 10, and 10, here it's 10 plus 1, 1. That means that we'll multiply by 3. The cyclic is what? 1 for 2. Well, this is not a clear example because there is some confusion here. For 6, when we multiply by 6, okay, we do a cyclic permutation of 3, 1, 2, 3. And you want to multiply by 6. You look at 6, it tells you to permute 3, 1, 2, 3. And that makes 8, 5, 7, 1, 4. See? You have the table of 1, 4, 2. 5, 5, 50, 57. There you go. The best way to prove this theorem is not by staying on Z, but by transposing the theorem into decimals and looking, do decimals of 1 or P equal 1 A. That is to say, we will find a period of n with the number A, which will return statically with the decimals. Well, I propose to prove this theorem now. So let's go. To prove this theorem, we have 10 which is in Z over PZ star because P is a prime different from 2 and 5. So we will call n its order. I affirm that m, a number, let's say a strictly positive integer, is a period of the decimals of 1 over P. Okay? So then a period, not the smallest period, so it is a period. If and only if, well, what? Well, obviously, if it's a period, then we have 10 to the m over P dash P. All decimals will be eliminated, right? 10 to the m over P is relative to 1 of P, a shift of m. So since it's periodic, we're going to have all the decimals that will cancel each other out. So we're going to have an element of Z. And conversely, if we have an element of Z, then it's necessarily a period. Okay? So that's if, only if 10 to the 200 until f1 is equal to P of certain K. K is the element of Z that is here. And so if is only if, well, 10 to the power of m is equal to 1 in Z over PZ. And we know that it's if n, since that's its order, divides m, right? That's the rule of the order. There you go. So, okay, we've shown that. Now, let's look at number 1, P. So it has a period n. So that means that there is an element up on page in its decimal notation at base 10 is written like this. And so we have the bar, right? That's what it means for the period, right? It's the repetition. Yeah. Usually it's the bar, it's something else, but here it is. So the di, right? I of 1n are numbers from 0 to 9. It means that 1 by C is equal to a constant 10 plus a constant zen plus adz, etc. Up to 10 to negative 2 and k going to infinity going to. And so it's geometric series with first term, a 10 to the lattice n and common ratio 10, now to the lattice n and n. So we know how it fits together. So that makes a 10 to the n, when that's 10 to the n, and by multiplying by 10 to the n, we have slash 10 to the n dash 1, which makes a equal to 10 to the n dash 1 p. There you go. And we have this element here, 4 now. So that's it. This element is indeed the element, huh? So the one we started with at the beginning. And well, it is indeed the element that we will find here in the period of 1 of pp. There you go. And now, well, if we have to look at this number, well, when we multiply this small number, a by k, it will make k x a. And if we choose a from 1 to p out of 1, well, we necessarily have k, which will be between 1 dot comes in. That is to say A and P strictly smaller. P dot P dot comes in, but P dot that makes 10 dot n dash 1. And 10 to the n1 is all nice. Well, there is n9 in its decimal notation. And this means that we are certain that K has n elements in its decimal notation. So be careful, these n elements, as we have seen, they can be 0 on the left. Be careful, there you have it. So now we are going to be able to multiply 1 slash p by. And here we are going to have the Ka bar, because Ka is going to have exactly n elements and digits. It is a number. K is an n-digit number. We have seen that. And well, you see in passing that when we do P on P, we are going to have 1 on the left, and we're going to find 0.9999 here, which is equal to 1 or 0.9 bar. That's good. Well, okay. So now we're going to say that K over P is equal to 0, and here we're going to have an n-digit number that's going to repeat itself periodically. Okay, this K is here in decimal, and we're going to look at when K over P and K prime over P, so these decimals that are K, are in permutation. So here we're looking at when K and K prime A are in permutation, and we're going to look at when a permutation, a cyclic permutation, because it's this element of K A that sends us to K prime A. So you see that we've transposed the problem here, which was a problem with integers, into a problem with rationals and the expansions of a pure rational numbers. There you go. And here it's practical because it's only here. Well, 10 to the slash p. When you do 10 to the rk on p, well, you will shift by r as such. You multiply by 10 to the rk, and you will therefore start with d1 plus rk. And then, since it is periodic, you will have the sequence periodically. So here, k prime over p. I write it like this. This index here is cyclical. Respect to mid. There you go. So, when is it at what they are in permutation? Well, if when we do it in rk on p, we'll find at the decimal level exactly the decimals of k prime z slash p. So, if and only, well, when we subtract, well, we have an element of z. That is the, to say now, if and only if, then to the r k belongs to p, z. So since we have not imposed the number r here, I can see that this is only this. K prime is in the same class as k modulo, the multiplicative, generated subgroup. So obviously, everything is multiplicative. Modulo the subgroup generated by 10. Okay, that's exactly what we've shown in z over bz star. There you go. And that's exactly what we showed. So there are as many numbers in cyclic permutation as there are classes here, modulo class. In Z, where PZ star modulo, the group generated by 10, the subgroup generated by 10. So that gives us P-1/1/n class, right? So P-1/n number, whose n decimal places are equal up to permutation. So that's something interesting. Ooh, but if we really want to do a magic trick, it is still interesting to have 10 that generates z over pz star. Because in this case, for all the numbers k and xa will be a cyclic permutation of the same number, and we will not have to change the number each time, which would be a shame for the magic trick. So we can ask ourselves the question, when 10 generates z slash pz, what are the p's such that we have this? So this is a deep problem, and I would certainly say deeper than all the problems of quadratic reciprocity, because there is no reciprocity here. You have a whole history of reciprocity where we know, for example, that 10 is a square modulo p. If we know that p is a square modulo, not 10, but 2 and 5, well, let's say 2 here is still frowned upon. But there is a reciprocity in squares. But on the other hand, in meshing, there is no such reciprocity. There is also a reciprocity. We can give meaning to a reciprocity for cubes and so on, but here it doesn't work. And we can't say that it generates here if and only if p generates modulo 10. That's it. It doesn't work. So Emil Artin, who was passionate about this profound problem, found nothing better than to attack the problem from the perspective of statistics. That is to say, what is the proportion of prime numbers p such that 10 generates z over pz star? Well, he conjectured that the proportion was the product of pr of 1 dash 1 for p factor of p1 1, which is about 0.37. Heveros mediduru, and here we can verify. It works for t and it also works for other numbers, but not for numbers. There are exceptions, but that was in his conjecture. And for 10, we have this. So this conjecture has not been proven, but it is true under the condition of Riemann's hypothesis, and even rather, a refinement of Riemann's hypothesis. On Wikipedia, we can find, for example, that, and then you can find it yourself with a calculation software, that for the first 500 prime numbers, if you test, the test is 10 in the form of z over pz. Well, for the first 500, well, you will have a proportion of 0.36, which pretty much confirms the hypothesis, the Dart conjecture. There you go. So then we can ask ourselves some questions. So yes, what are the others apart from 7? Well, apart from 7, we're going to have after 7, well, not third, because that's in order, well, it's index 2. But 17 will work. So you can do it with 17, you can do it with 19 too. So you can have a couple of numbers where you can have the cyclic permutation. How for 17, you're going to have a 16-digit number. Be careful, there are zeros in front, but it's still 16 digits, and on which you're going to have a permutation that you're going to multiply by cases from 1 to 16. There you go. And then for 17, well, you're only going to have 9, 16, 9s. There you go. We can also ask ourselves the question, can we do things with 1LN? Does it give us new numbers with cyclic permutations? So the answer is yes, but it's still quite rare, because we want 10 to be a generator, but here we already know that it's cyclic. If this group isn't cyclic, there's no chance of having a generator. So we have to look at when z over nz is a star and is cyclic. And here, in addition, since n must be prime with 2 and 5, n must be odd. And well, z slash nz with an even number is cyclic. Well, if and only if n is the power of a prime number. So you can see it for 49, right? You do 140, and you'll have what? This time it's a period of length phi of 49. Okay? So root to not. That is, if I'm not mistaken, 42. There you go, you can check it. And it will give you a cyclic number, but you won't take all the cases from 1 to n-1 to 1. That poses problems, is less magical. There you go. So, okay, we'll stop there. We've pretty much covered the issue.